We've got quite a lot to get through today, so I'll get started immediately. I'd like to acknowledge the Gadigal people of the Eora Nation, the traditional custodians of this land, and pay my respects to their elders past and present. I'm David Briggs, Vice President and New South Wales Divisional Chair of the Colour Society of Australia, the Australian member body of the International Colour Association, and co-chair of the AIC Study Group on Art and Design. The Colour Society of Australia is a 100% volunteer-run, not-for-profit organisation and welcomes all to its events and membership. This event continues a series of webinars organised and presented free of charge by the Colour Society of Australia, New South Wales Division over the last 3.5 years. If you'd like to support us and gain unlimited access to our recordings of previous webinars and conference presentations, please join us today. Greatly reduced student concession and regional international rates are available on our website. We've had a great response of 146 registrants from 19 countries around the world. So we're asking everyone to stay muted. But if you have questions for John, please submit them in the chat. There are 2 scheduled question breaks within the proceedings, and we'll try to get to as many as we can in those breaks. John Pretorius holds a PhD in pure mathematics from Cambridge University, and with former CSA Treasurer Werner Dietrich, co-created the paint engine software behind the Golden Paints virtual paint mixer. He studied painting at the Julian Ashton Art School and is a former president of the Colour Society of Australia. John is also a founding director of the Simon Murray Mathematics Competition, the International Mathematics Competition for undergraduate students. So please take it away, John.
Thanks very much, David. Look, I'll get straight into it. As David said, there's quite a bit to get through today. So let me share my screen. Let's see. There you go. So what we're going to be covering today is listed on your screen there. I think one of the main points that I'd like to make is, as all painters know, painting is hard and a lifelong endeavor. What I'm trying to do today is to give those that are beginning and maybe some of the way through their painting career, replace the questions they currently have with some new and more interesting ones. I hope to do it in a reasonably simple, structured kind of way. So we will start off just looking at the absolute basics. When you first start painting and you run into all the different paint manufacturers and paint tubes and labelings and so on, what to make of those, what's useful information, what's not. Then we'll look at the language of color. Some of you will know Munsell space by now, some might not. I'll very briefly touch on that, really just to set us up to start looking at paints, which is really our big common interest. And in points 3, 4, and 5, you can see I'll be doing it fairly systematically. I guess it's as a mathematician, I can count 1, 2, 3, many. So I start with single paints and talk about them a little bit, how to think about paints versus color, talk about mass tone and undertone and so on. Then pairs of paints, tinting, toning, and shading. Again, all of this will be presented in a 3D way. So because we have so many paints and so many ideas to look at, it's actually more efficient to just do that in the viewing software. And I think it's very important to reinforce the idea that for most purposes, color has at least 3 dimensions. It's really got more, but 3 would be the least you need to think about all the time when you're painting. Once we get to triples of paints, we'll start talking about palettes. I'm not going to tell anyone what palette they should use. I've used different palettes myself over time. I think more important is to acquire some of the tools to think about your palette construction that you might need in a particular context on a particular phase of your career. And then I see number 7 has magically switched to number 1, which in some ways it should be. It's color matching strategy. So when you're trying to match certain colors, which of course you do a lot of the time. It's not the only thing you do when you're painting, but it's one of the important things. And suddenly it'll become clear that everything we were talking about earlier on, the tinting and toning and shading in particular, are very basic tools for a systematic way of matching colors. So this goes back in one form or another to Frank J. Riley, and I'm sure to painters through to antiquity. Frank Riley is known for doing it in a very consistent way and teaching it to generations of students. David and people like Graydon Parrish in the US teach this or a variation on this all the time. Today we'll have time to look very carefully at one example, and hopefully that will act as a blueprint for how you'll do color matching, generally speaking. So this part of the talk, which will go up to the single paints, point number 3 there, should last about 45 minutes. Then we'll have some Q&A to clarify things if you, I believe Veronica will be curating that. We'll have a brief tea break and then another 40-45 minutes on the rest of the painting issues. So the second half will have a lot more of the 3D viewing. So let's get on with looking at the paints themselves. So this is a typical, I just pretty much plunged into my collection of paints, and it's a mixture of acrylics and oils. And what I highlighted there are typical things that you find when you look at paint tubes. So the phthalo blue has a PB154, light fastness 1. It talks about ASTMD something or other. It's got a reference to cost there. The yellow oxide talks about PY42 and a cost reference again. Over here we can see the golden open, the second from the left. It has all sorts of indications about transparency, whether it's matte or not, thin, tinting strength, and so on. So I think we've all looked at these. We all, I'm assuming people have. I certainly in the beginning didn't understand what they all refer to. So let's go through it one by one. Here's a little bit more detailed information. So I think the first point to make is everyone should know that the reputable manufacturers all do have very good websites where they have a lot of detailed information on the paints. In fact, sometimes a little bit too much. I think looking at this, the Natural Pigments website, for example, they've got an enormous amount of information, which obviously is interesting from a technical point of view, but it's hard to be convinced that every single piece of that information is going to make a big difference to your painting practice. So it's a matter of being able to sift through that as well and pick out the bits that matter to you. And there we go, just more examples. Langridge, the Australian brand, it's oil painting. Talks about the pigment, gives a chemical name, various classifications, again, some numbers and so on. ASTM is referenced again, and so on. So having gone through all this, I think one of the most important points to realize is that labeling is really not standardized at all. And almost all elements of the disclosure is voluntary. There's a really great article written by Sarah Sands in the Just Paint, which you can find online. Sorry, Wrong Umber, part 1. And so on the right-hand side of the screen, raw umber is one of the most basic paints that everyone uses for a number of different reasons. And that just gives you a short rundown of all the possible contents that might be packaged under the generic name raw umber. So a lot of them would contain pigment brown 7, and we'll talk about these pigment numbers in a minute. The natural brown oxide, it does occur in there, but many of them actually have additions to make it greener. And in these cases, they've just taken the brown oxide and added some green pigment to it to give the typical green sheen that you have with raw umber. In some cases, like this one here, there's in fact nothing quote unquote natural in there whatsoever. There are synthetic equivalents, and there's 4 different pigments making up the raw umber. So naming doesn't give you a huge amount of information. Manufacturers use their own terminology. So light fastness excellent, quite possibly has very specific meaning when it comes to that particular manufacturer, and you might get to know them over time, but it has no standard interpretation in the industry. There is a light fastness standard, and we'll talk about it in a second, but quite often the wording is either missing or, as I say, varies by manufacturer. And then finally, especially for people that are worried about exactly, are they dealing with something that's really student grade or something that might contain something that they allergic to or irritants, the fillers, extenders, dryers, all that sort of stuff is quite often simply not listed. So unfortunately, not a good start in terms of the information you can get off a typical paint tube. So let's start with the absolutely basic thing, the safety part. So earlier on, let me just flick back. Over here on the right-hand side, that's a sign, that's a stamp that you quite often see on many paint tubes, and that refers to, that's the ASTM safety standard. And what that is really the quote there: "This practice describes the standard procedure for developing precautionary labels for art materials to provide chronic health hazard and precautionary statements based on knowledge that exists in the scientific and medical communities." So it basically forces the manufacturers that adhere to the standard to disclose some absolutely basic information about pigments that really might be harmful. ASTM International is the American Society for Testing and Materials. They've got many standards, and typically people that companies that sell in the US need to adhere to that and make a declaration as to whether they're adhering to that or not. So one of the many things the standard doesn't do is obviously it doesn't tell you that the materials are safe to use. It doesn't disclose materials that are in there in far smaller amounts, or about which they're not specific information in the scientific and medical communities that it's hazardous. It doesn't give you any quality guarantee, so it doesn't tell you whether pigment concentrations are high, for example, one of the things that people think about. And it doesn't tell you anything about permanence or light fastness. So it's, in some general sense, it reassures you because it means that, it's a large manufacturer. They take their responsibility seriously. They try to sell in the US. So you have that kind of generic reassurance. But in practice, it doesn't really tell you anything that you need to know. Actually, that's unfair. It is very important to know the pigments, and it does force them to disclose the pigments, but that's about it. Next one is the pigment color index. So there's two levels to this one. In fact, point number 2 there is the really detailed number. So if you dive into the Natural Pigments website, or I saw it on Language as well, and Golden, they give you the CI, the color index constitution number, and that can really take you into chemical databases if you're really researching the pigments properly. For the purposes of painters, the generic name code, the ones that are prefixed by these by the P's, are the ones that you normally look at. So PW for whites, PY yellow, PO orange, red, violet, and so on. And then the PBRs and the NBRs that are typically for the umbers. So that is the number to look at, and that gives you a basic point of comparison between paints from different manufacturers. I might jump ahead at this point and just refer you to this website, the artistcreation.com. There are much more detailed information sites giving you specific information on each of these pigments, but they tend to be behind paywalls. So this one is the best one that I've been able to find. I think I've got a snapshot of the front page of the landing page there, and that gives a lot of information, not just on the pigments, but in which what kind of binders they be used, so whether they're used in oil painting or acrylics, watercolor, and so on. And I think it's reasonably up to date, and for most purposes, from an artist's point of view, that is probably as much as you want to know about this before getting on with your painting. There's a very nice blog that was written by Evie Hatch, which you can find, which I reference over there. Jackson art and talks about this in greater detail. So the main point that I want to make here is the first thing that I do, at least when I look at a tube of paint, is exactly is it PW4, is it PW6, and to slowly build up my knowledge of the pigments that occur in the paints that I really like to use. The next question is the light fastness of pigments. So there's also an ASTM standard there, which is D4303. There are various methods, test methods that are prescribed for the manufacturers to use. So exposing a paint to the sun under glass, radiation from artificial daylight fluorescent lamps, xenon arc light fastness, and so on. And then, so essentially what happens is you create a paint sample, one half of it you put away somewhere dark and safe with no light exposure, and the other one you expose for a certain period. At the end of the period, you measure the color in both, and then you've got some numerical means of comparing and seeing how much they've shifted. If it's shifted a certain minimum amount, you can say it's ASTM 1 or 2 or 3 and so on. So this, in theory, sounds like a good thing. Oh, well, it is a good thing. The devil, though, is in the detail. And I think what people realized fairly recently is that there are issues with the way that these tests have been run. They're not consistent between manufacturers, and they're not consistent over time. So to show that in more detail, this comes from a talk at the 2018 Munsell conference in Boston, and the entire talk is available online at the link that I give you there. And in particular, it highlighted testing issues with organic pigments. So I will define organic and inorganic in a minute, but just say there's absolutely major category of pigments where if you look at their testing results across different brands, so here we have how many, 11 brands, then you can see there's tremendous difference between the different. This DE is the change in color, and if you look at the same pigment tested over time, again you can see a lot of variation. There's a cutoff for ASTM 1 and there's a cutoff for ASTM 2, and over here it was 2 and 3, and it's just all over the place. So I think that dented people's confidence quite a lot. And the committee that looks after this went away and said they'd come back in 2023. And so they're due to report, but at this point they haven't reported yet. So before there is a conclusion there at 6 what to do when you're having to deal with inorganic and organic pigments. But the first thing I want to say is just to clarify what we are talking about, and this is very important. I think generally speaking, when you're thinking about light fastness, the way pigments behave, and just wanting to understand more about their history, because certainly when it comes to paint pigments, it started off being more inorganic pigments, and in recent years it shifted to a tremendous amount of organic pigments that are very high chroma and just can do things that we used to not to be able to do. So the inorganic ones are basically various salts of metallic salts, synthetic oxides. They include the cadmiums, ultramarine, cobalt blue, chromium oxide green, literally all the iron oxides, yellow iron oxide, red iron oxide, the cobalts, the manganese, all of those are inorganic. The organic ones are put together, basically they contain carbon chains or rings, and all the names that are hard to pronounce in practice: the anthraquinones, the thiocyanones, the pyros, the quinacodones, the azo pigments. I think there's a bit of a discussion whether Prussian blue technically is inorganic or organic, but the organic ones are more modern pigments, and they are the ones under discussion here with respect to the ASTM standard. So the question is, if you, a lot of the paints that people use at the moment either are fully organic or have organics in them. So does that mean you now suddenly have to stop using them? I personally don't think so. I think it's worth, if you're really worried about light fastness, just keep your paintings out of UV light. That's the first fundamental point. UV light is the most high energy light. It's the one that is most damaging, just as it's damaging to skin, it's damaging to pigments and to paint layers. So don't expose it to too much light. And then if you're very, very worried, use them sparingly. One of the things that became clear in these tests is that the organics are especially vulnerable in tints. So if you use them neat as in a glaze, for example, they actually last better than if you mix them with titanium white or other white pigments. I think you can almost think of that as the organic pigment being on a beach and literally getting radiation from all sides when it's intermixed with the titanium dioxide particles. And so sometimes it's better to use it on its own rather than mix it into a tint if you are extremely concerned about the light fastness. Next topic would be the permanence of the paint film. So in this case, there isn't really, or at least to my knowledge, a standard that is even reasonably widely used. So it comes down much more to what each manufacturer discloses or how they want to grade it themselves. So permanence in this case is a wider concept than just light fastness. So it talks about the degree to which your pigment and your paint film is resistant to acid, alkali, temperature fluctuations, chemical reactions. You know, sulfur in the air used to be a big problem when there was lots of pollution in the cities. Physical stresses, you know, whether you paint on canvas or whether you put on a rigid support. So it covers an enormous range of things. And so, you know, to simply say permanence, you know, good or excellent, in some sense would potentially cover a multitude of areas and sins. And really all you can do there, if that does worry you, is first of all, get familiar with the particular manufacturer's way of disclosing this, how they talk about it, what technical knowledge they impart. And again, there's just simple differences between painting on different supports. So rigid support seems to be fairly consistent, especially in oil painting, a much safer place to paint than canvas. So this is fairly well established at this point. Rigid support is less subject to temperature variation issues and mechanical stresses and so on. It's not rocket science to keep your paintings away from chemical reactions in UV. We've already talked about that. In oil painting in recent years, zinc oxide has become quite a big issue. So zinc oxide is a lovely white. It's wonderful to do tinting with. But what was found is that in the context of oil paint, and this is not acrylic or any other context, in the context of oil paint, once it cures, it tends to potentially start flaking or induce flaking in the paint layer. And this is especially a problem because painters use a great deal of white. Titanium white is probably the main one, but in an attempt to improve the properties of the titanium white and make it more like classical lead white, and have just general mixing and mechanical properties that were better, manufacturers added in zinc white. And now, as I said, we're finding that this is potentially a significant problem. And to the extent that testing has been done, they haven't actually found a safe lower limit for the amount of zinc oxide that can be included. And consequently, I think there's quite a move now to, well, obviously, first of all, disclose if it's included in any white or in any paint. And secondly, very often people prefer to avoid it entirely if they can. again, if you're painting on a rigid support, it's quite possible that it's not so bad, but on the tests that I've seen are really quite astonishing at very low levels. If you start bending, for example, a canvas, flaking starts occurring. So that's an example of something that really affected the permanence of the paint film for a number of paintings, for many paintings over the past 20, 30 years. And of course, people were simply not aware of it. And there was nothing in any disclosure on the paint tubes that was going to help them with that. So overall, I probably don't, probably doesn't sound incredibly optimistic. I think some of the disclosure about pigments is very useful, and it's really worth getting to know the pigments in your favorite paints. The light fastness disclosure is useful up to a point. It's useful to know that many of the inorganics are just naturally stronger or more light fast than the inorganics. However, many of the modern inorganics have been developed in the context of, for example, the car industry and coatings for cars. And obviously, those are exposed to very extreme circumstances over time. So some of them will turn out to be very, very light fast. The problem is we're not absolutely sure which ones. And so for that reason, it's worth, if you do worry about the longevity of your paintings, to have comparatively conservative studio practice. The one thing I haven't mentioned here, because it's a massive topic within acrylics and even just in oil with these few binders, but there is a bit of a ranking among the oil binders. So if you're looking at linseed oil, walnut oil, poppy seed, and safflower, among those, the linseed oil is a very well, I mean, it's obviously been around for hundreds of years, and it's the most well-studied one and tends to be a very good binder. I think safflower oil is the one that recently people have had some concerns about, because it's not actually a drying oil, it's a semi-drying oil. And so some of you will be aware of cases in paintings in the past 20 or 30 years where people have applied essentially impasto paint in safflower binder, just massive amounts of globs of paint that have been put on the canvas. And in years afterwards, they found that it started weeping and the safflower oil would come out. So this by no means happened with all safflower paintings. And in most paintings that you do, you're constantly mixing the safflower with linseed and or walnut and or poppy seed anyway, and applying it thinly. But it's something to be aware of. It's something to look at when you're buying your oil paints, especially. What is the oil painting? What's the actual medium? And what might that mean if you intend to use it in an unusual way? So I think that pretty much covers what was probably a slightly boring but necessary part of the process, and brings us now to what's more interesting for painters. We're just talking about actual paint and making color with paint. So I'm going to try and cover in this first part on color spaces pretty much all of color theory and color space theory in one slide. So you'll appreciate that I can't go into technical details too much. I guess everyone is aware of thinking about human vision, that our color vision fundamentally is determined by 3 different kinds of cones in the eye. This is not the place to try and explain how that information is combined and recombined and used all the way back into the brain to create the sensation of color. I want to concentrate here on the number 3. A physicist looking at all this would say there are 3 degrees of freedom. There are 3 channels of information, and both our brain when we're processing what we see, and also then our brain when we talk about these things afterwards, tend to reorganize those 3 channels into 3 useful channels, 3 channels that apply to the situation at hand. So I think if we look, everyone is aware of, or I think everyone would have heard of RGB, red, green, blue, which is used in the context of screens, additive mixing of light. So you have the three there. You have cyan, magenta, and yellow, which which would come up in the context of filters and ink in printing. Of course, it's usually CMYK, but the K is there kind of for a physical reason, which is that you just want better blacks. It's not really a color theory thing. You have lab space. So what I have there is L star, A star, B star. That's a mathematical model of color sensation, which is actually the basis for the displays in the rest of this presentation. But the main point there is, again, there are three letters. There's lightness, there's green, red dimension, and a blue, yellow dimension, which is the B. So again, three. In the digital world, there's HSL, there's HSV. In the color theory world or color science world, XYZ, little xyz, etc., etc. The point is there's three occurs over and over again. That doesn't mean that there are only actually three dimensions to color. There are more dimensions. These three are most apparent when you have very, very controlled viewing conditions. So if you don't have huge background variation or what's in front of you, there's no temporal variation, so strong changes over time or changes in mode of perception, all those things really matter and add more dimensions to perception of color. We will stick to the middle ground and talk about three main dimensions and just develop language to describe each of those dimensions. So in this context, I want to mention the natural color system, Munsell and lab, which has already come up. The natural color system is a Swedish system. And the application there is color communication between designers and manufacturers, retailers and customers, as they would say in their blurb. I think there should be an animation of the of NCS. So we've got 6 colors there: the red, green opponents, the blue, yellow opponents, and then the white and black. And then there's a page, sort of a triangular page, which obviously in this animation gets displayed fairly quickly. And that maps out one 3D view of the color world. And you have their blackness or whiteness and chromaticness. It's got its own color language. And in fact, everything that I do in this talk, I'm very convinced I can translate into NCS terms, because you always can. It's just not the most convenient from a painter's point of view. So that brings us to Munsell. So for those of you that haven't come across it before, Albert Munsell was a painter who in the start of the 20th century tried to organize colors in 3 dimensions that make sense for the traditional painter's process. So there's dimension of lightness or value, and then 2 dimensions of color. And those 2 dimensions are the hue or the color family. So that talks, about the bluishness, reddishness, greenishness, or yellowishness of the color. And then the chroma, which is the strength or the intensity of the colors. And he tried to organize it into fairly equal perceptual steps. Now, it's good to keep in mind that when it comes to this terminology, there are very specific technical interpretations for words like hue or chroma. And David, for example, gives very rigorous reference to the CIE definitions. For us, we need to be sort of on a middle ground here, I'd say. So color is a very general word, and we're going to use lightness, hue, and chroma in quite specific senses for the rest of the talk. Now, lab space actually developed in parallel with Munsell. There's a lot of commonality between them. It happens to be a space that is kind of, in terms of numbers, mathematically speaking, a little bit easier to deal with. And so the displays in this talk will be in lab. And let me just flick forward so you can get a visual idea of what I'm talking about. So first of all, just talking about Munsell again. You have the lightness scale, which is the vertical scale, 10 at the top, which is perfect white, and then 0 at the bottom, which is perfect black. Sorry about that. Going around the circle, the hue circle, these are color families I mentioned. They're quite particular ones to Munsell. He had some, he was apparently not aware of the word orange, so he needed to say things like yellow, red, and red, purple. But at the same time, it gives a nice consistent, there's a very consistent terminology for labeling colors around, for labeling hues. And then on each of these slices going outward, you've got the grayish colors near the middle, and then the highly chromatic, the high chroma colors towards the outer edges. And this is a very pretty slice into sort of a physical representation of Munsell space. I tend to think of the lightness levels as almost being on the same story of a building, and then near the elevator shaft in the middle are your grayish colors, and as you go out towards the windows on the side, you get the much brighter colors, the more chromatic colors. So very similar to this, but simpler, hopefully, is the color space that I'm going to be using for the presentation here. So exactly like Munsell, your vertical axis is lightness. So you've got perfect white at the top, and perfect black has disappeared into the perfect black space. You've got horizontal axis here. So the one axis are essentially the greenish reddish opposition that you also find referenced in NCS, and the blue one over here, or blue yellow, running across your screen from top left to bottom right. That's the yellow blue dimension. And just for easy reference, I've actually inserted this hue circle. So I could have just let these axes run out into infinity and shown absolutely nothing here, but just to remind ourselves roughly where we are on the hue circle, and then the slightly transparent part of the circle, to give ourselves a constant reminder. They're crossing there right in the middle. So this would be like 100 and this would be 0. So it's crossing at 50, which is quite close to a Munsell 5. So the lab lightness scale and Munsell lightness scale are very, very similar. If not, they're not exactly the same, but they're close enough for our purposes. So we get on to paints. The first point that I want to make, and again, this is entirely obvious to somebody who's thought about it for a while, but it's worth pausing just for a minute. A paint is more than just a single color. So I'd be the first person to say, oh, in this context, you know, I need a blue or I need a yellow or something. But really, as you know, when you spend any time with paints at all, a physical paint has many more dimensions than just the color of its mass tone. So just the terminology there, mass tone versus undertone. If you look here at this Langridge paint, the thick, opaque version of the paint, that's the mass tone. The undertone is essentially when you smear or draw it out and you've got an extremely thin film of the paint behind. That sometimes has quite different hue. Sometimes it's not entirely clear whether it looks different simply because of the background, which is having more of an effect on it. But sometimes there are significant hue shifts. And in this case, it does seem to me like, to my eye, the mass tone is a little bit more reddish, and it becomes much more clearly yellowish when you go into the undertone. And then glazes, well, people mean different things by glazes, but here's an example from Golden, where they have a transparent medium that is mixed in with a quinacridone in a 1:10 ratio up there. That can give quite similar effects to just doing an undertone, just doing a drawdown. And again, I think, to my eye at least, there is some hue shift from the mass tone into the glaze. And so that's already, we haven't even started mixing the paint yet, and already it's manifesting different colors in different situations. I think it's something that we're especially familiar with in the yellows, depending on whether the yellows are transparent or opaque. They really don't look the same against different backgrounds and when they interact with other paints. Now, having said all that, there are some things that are common to all paints of a similar color. So, for example, most reds become more bluish than when they mixed with a white paint. That is partly because of a basic physical reason, the way the reflecting spectrum works for red paints, and blue that gets added in the moment some white gets mixed in with that red paint. So it's going to be an almost universal thing that a red becomes more bluish when you mix in a white paint. So something that I'm implicitly referencing here when I'm talking about mass tone and undertone is transparency versus opacity. So we're now sort of getting closer to probably the most technical part of the talk. So I'm perfectly happy if people that don't love numbers and graphs tune out. We're going to be talking a lot more just about paints later on. But I think it is still of interest to some of you that want to understand exactly what the differences are between transparent paints and opaque paints and how they interact. So 8 years ago,
sorry, Jean, we're at 40 minutes, just letting you know.
Oh, great. Thanks, Veronica. So here's a graph from a talk that I gave 8 years ago to the Color Society. This is a Pyro red paint, and it runs through all the different wavelengths, visible wavelengths, which roughly normally is counted to be 380. In fact, goes up to 780, but almost runs out in most people around the 700 mark. And it clearly shows how this paint absorbs a lot of light in the blues, the cyans, greens, yellows, even some of the orange, and then starts reflecting very, very strongly into the red. And that's why we get the red color sensation when we look at it. But that graph tells us absolutely nothing about opacity or transparency. You can't look at that and say, oh, I can now tell you for sure that Pyro red is transparent or opaque. And the reason is that we need to think harder about what actually happens in the paint film when light enters the paint film. So I'll tell you the answer in general terms, which is that we need to distinguish between the scattering and absorption. So scattering is roughly what we think of when we talk about reflectance, but it is literally how the light bounces around off the particles inside the paint film. And then the particles can also simply absorb the light. So when a light hits the particle, it either gets absorbed or it gets scattered, so it bounces back in some random direction, or it goes straight through, like as though the particle or the dye or whatever it was simply wasn't there. And to understand transparency and opacity properly, we need to keep track of scattering and absorption separately. And one of the big breakthroughs in the 20th century was the creation of the Kubelka-Munk model, which is a mathematical model for paint mixing. And the Kubelka-Munk model made it very clear how important the ratio between absorption and scattering was in determining what light comes back at us, what light is ultimately reflected from that paint. So thinking about this, if absorption is very, very low and scattering is very, very high, this is near 0 or something, and this is near 100, this is going to be a very small number. And there's a formula for turning that into a very big reflectance. And conversely, if the absorption is very high and scattering is very low, then it'll be a big number divided by a little number, and that very large number turns into a low reflectance in the Kubelka-Munk formula. So I'm going to just flick through those slides. As I said, I fully understand that Not everyone is interested in this, but I do know that there might be a couple of people in the audience with an interest in this. Just a brief version of the KM model. And here we have scattering and reflectance graphs for titanium white, which shows flat scattering, very low absorption, and as a consequence, almost perfect reflection, except maybe on the blue side. Carbon black, on the other hand, has incredible absorption, very high absorption. Funnily enough, it does scatter, but the big thing is that it scatters a lot less than it absorbs. And the gap between the two stays constant, which gives us a flat, low reflectance. So here's the formula. Skipping the formula, I think we need to go to something a bit more practical just before the tea break. So I did a tea experiment. So in this experiment, I made 5 cups of tea, and I added in varying amounts of milk in the tea, starting with 1 teaspoon and ending with half a cup. And the expected thing happened. And after that, let me just take this one out of the way. I'm sorry, everyone. I'm aware that my whole desktop is visible, but I needed to bring up these figures. This is from our tea experiment. So let me explain what's happening here. If I can just get, there we go. Now we see the 3D properly. This was the color measurement of just the pure black tea. This was with 1 teaspoon, 1 tablespoon, whatever that was, 1/4 of a cup, half a cup. And you see the same effect that you see with very many transparent paints, which is that you start with something that's very dark. It looks as though it's quite close to being gray, but for something that's very dark, it actually has a surprising amount of color. That tiny distance there is actually quite a lot of chroma for a very dark color. And then the moment you add in the much more opaque white particles, the light doesn't have to go quite as deep into it to start coming back at you and show you what the color is, and the color just explodes. So the chroma is, the apparent chroma really, really expands a lot. And then, of course, at some point, as you add more and more of the white starts dominating, and you find that, just looking at this from the top, I'll just slowly flip that over. So you can see the chroma increased, got more colorful, and then the chroma starts decreasing as it gets lighter. What we also notice here is that you get a hue shift. So there's a distinct shift towards the yellow side as it gets lighter, and there's more milk added to the tea. And again, this is a really characteristic thing that happens over and over again with transparent pigments or semi-transparent pigments. So I think that's probably as far as we want to get for before our first Q&A. So I'll hand over to Veronica.
Great, thank you. I have got a couple of questions, and just going back to Peter Donahue, he said, "Hi, I'm curious about your thoughts on walnut oil as a binder. Thanks." Which is a question that I had for you when we were going through this.
Veronica had to suffer through this presentation once before, and I hope it's better for that. Look, to the best of my knowledge, and I'm not a chemist, I'm really not an expert on this, but to the best of my knowledge, linseed and walnut oil are both very good binders if you're oil painting. Walnut oil obviously dries more slowly than linseed oil. But in terms of the ultimate paint film that's formed, I don't think that there's a major difference. So the concerns are normally more with the oils that are used for blues or for whites, like your safflower and your poppy oil. I'm not quite sure where I picked this up, but in my mind, there's a kind of an ordering to this where linseed and the walnut would be on the same level, poppy seed maybe not quite as good, and safflower really the one that you need to do some soul searching about.
Right. With regard, you keep on mentioning it. So if anybody else has got any questions, please go ahead and put them now. There is another question. I'll leave mine till last.
Sure.
I'm curious, what is fluorescent color? Is it super high chroma, saturation, reflectance, or what and how does it fit on the Munsell color wheel? This is Progressina.
Yeah,
Would you
look,
like
that's a very good question. I think fundamentally what happens with fluorescence, and again, in my fairly limited understanding, but fundamentally what happens is you get light of one frequency, sometimes a non-visible frequency, which falls on the pigment. And then that gets absorbed and then re-emitted as a light at a different frequency. So all the ones where, like when I was talking here about Kobelka monk, you might have light coming in at 500 nanometers or something, and then what happens is very straightforward. It either bounces in all directions, it gets absorbed, or it gets let through. What happens with fluorescence is it gets absorbed, but the material actually re-emits light, possibly invisible, but the important ones are obviously the visible ones at a different frequency. And then, frankly, pretty much everything I said gets scrambled, and you need to be much more careful in your modeling. So what I've just described really would not work as it is for fluorescent pigments.
Okay. I have a question with regards to zinc oxide on titanium white tubes.
Yeah.
So I've got a mixture of titanium white on its own, PW6, and then I've got some with sunflower oil. So the titanium white with sunflower oil should really be thrown away.
Well, not necessarily, just not used in
large quantities.
In stick layers, yes.
Yes. And out of the titanium white and zinc oxide, I have one with alkyd.
Mm-hmm.
And it's also based on sunflower oil.
Right.
So because of the alkyd, it should be a stronger, in theory.
Look,
titanium white.
Yeah. Georgia Hannon has some very good material on this on the Natural Pigments website. So I think if you really want to look at that in detail, you should read what he has to say. I personally like the alkyds just because they were formulated in again an industrial context, much more heavy use than what they normally used for in the fine arts context. So the alkyds are quite strong. If you have an alkyd that's based on safflower oil, it means it's been modified. And that's where my chemistry knowledge runs out. It's been modified. It is most likely significantly more durable, possibly even than linseed oil. But obviously, we haven't got 500 years worth of data on how that paint film evolves. And saying, I mean, it's not just a cute thing to say. The oil paint film actually keeps evolving for decades and hundreds of years. So it does matter. And we don't actually know, even with the best binders from the 20th century, what they'll be doing in the 22nd century. Now, many people might say they don't care, and I have some sympathy for that, but there are more important things to worry about. But in terms of if you do think about those things, then linseed oil and walnut oil are the proven ones. Poppy seed oil in moderate amounts. Safflower oil, well, it's a semi-drying oil. For my own, especially for underpaintings and in thin layers, using the alkyds, I think, have a place. But alkyd painting as a whole, some people don't like the odors. It's certainly chemically much more complex product than a simple paint ground in linseed oil. And I do understand that not everyone likes that.
We have got actually now a few more questions. Would you like to continue? Should we have a break?
Yeah, absolutely. I think we've got another couple of minutes for this.
Okay. Melissa Carmen, thank you so much for this presentation, Sean. The question that comes to mind is this: how is the path through lab space ascertained for any particular paint? Particularly, does one need to make physical samples which are tested with a spectrophotometer, excuse the pronunciation, to understand its particular behavior through the color space?
Look, yes, in principle you do. I mean, obviously, what painters do and have done for hundreds of years is to get the paints they're familiar with, work with them a great deal, and implicitly all this knowledge is in their painting. They can do this stuff. They don't need to be told this in 3D color space. 3D color space, I think, is a really useful way to think about it if you have the luxury right from the start, and to use that language. To create these paths, yes, definitely, there's a lot of spectrophotometry behind it, a lot of calibration of the model and so on. But the point is that's been done. So in the case of the virtual mixer that Golden has on their website, it does all that for you, and it gives you the RGB values, or it gives you a representation also of the mixes on the screen. The only advantage that I have is I'm able to do these things fairly quickly, so I can do hundreds of them in a very short time. So I'm simply graphing the outcome. But the short answer is most of that is sitting behind the virtual paint mixer, and so you can just use it as is.
Wonderful. Peter Donahue has got another question.
Sure.
Is there a technical scale or formal way to describe the tinting strength of a given pigment?
Yes, there is. I mean, in fact, there are some numerical standards for that, and I believe on their website, Golden would display numbers that quantify the tinting strength. I think the one issue with the tinting strength is that really it's a balance usually between two paints, and that balance, like we all know, phthalos have very high tinting strength, and they're going to tint anything that they interact with in a very marked sort of way. To get a single number that quantifies that with respect to every single other paint is actually the tricky part. And so, I mean, we can continue this discussion offline, because I certainly I've created a couple of these measures myself. But for the purposes of this presentation, I think definitely for practical purposes for painters, what I've done is to have set mix ratios for all of the paints. So I might as well, I'll give you a skip ahead. I'll share my screen in a second. So this is a little preview of what's coming after the. There we go. So can you all see the? Can you see the?
Not at the moment. No.
Not at the moment. Oh, okay. There we go.
Now we can.
Okay. So this is a representation of a mix between bone black and titanium white. And what you can see, I've done it as a series of beads traveling from the one to the other. But each one of the larger beads represents a specific ratio. So for example, so let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, so there's 7 of them. So the top one here would be a 1:30 ratio. So 30 titanium white, 1 bone black. And then the next one would be 1:10, 1:3. That's a 1:1 mixture. And then 3:1, 10:1, and 30:1. And to use exactly those same ratios on all of the mixing paths. So every mixing path that you'll see in the presentation will have those ratios. And now you can have a look at what happens at the one closest to the titanium white. So you see, basically, you start with titanium white and you add a tiny bit of bone black, and you see how far you get pulled. Or conversely, you start with bone black and you add a tiny bit of titanium white, and you see how far you get pulled in that direction. And so when you sort of compare those two, you can see, well, between these two pigments, the bone black essentially has a slightly stronger tinting strength for our purposes. But the spacing is very even. So, I would actually think of that as being a very well-behaved and not too strong tinting interaction. So Peter, I'm sorry, it's quite a wordy response, but I'm afraid I don't think there's the honest response is a simple one. And what will be trying to do here is to just show relationships between lots of pairs of pigments.
We have one more question. I don't know if you would like to answer it now.
Sure.
Oh, sorry, it just moved on me. This is from Marta. When I've expressed concerns about the light fastness of certain pigments, one of the standard answers is just frame it behind UV glass. To what degree does UV light improve or modify the light fastness of pigments in general, and especially with the pigments that are rated below excellent? I think she means to what degree does the UV light glass? Or
yeah, look, I think, again, as far as I know, I think that's probably a reasonable approach, because the UV side is the most energetic side. So as you go through the light spectrum from short wavelengths to long wavelengths, the short side is the blue and the UV side, the long wavelengths are the red side. The energy drops off. So the individual photons that actually hit the paint film reduce their energy. So basically you're worried about the blues and the UVs. Those are the high energy ones. When they come in, they're going to do, they're essentially like bullets. They're going to do the worst damage. If anything is going to damage in the incoming light, it's going to damage your paint film. So yeah, I think that's a reasonable thing. That's partly why I said, you know, if you're really worried, just keep your painting out of direct light, keep it away from UV as much as you can, or reflected UV. And certainly if you've got a proper UV filter in front of it, that should do that. So yeah, I think on general terms, it's perfectly reasonable. That doesn't mean that you can't have some weird organic pigment that for some reason at a particular green frequency acts, does something strange. That's different. But as generic advice, I think that's reasonable.
good. Thank you very much for all that. I think it's tea and coffee time.
It definitely. Thank you very much.
Okay, so we have, what is it? Would you say it's a 5-minute break?
Yeah, just sort of, yeah, five,
Apart from
7-minute breaks. Yeah.
10-minute break? Yeah, okay.
Sure. Thank you.
10-minute break. Thank you very much, everyone.
Sure. So now we're going to be talking about combinations of two paints. And just to remind you, I hope we managed to get through to the paint, the color matching exercise at the end, during which you'd be using both toning and tinting and shading all the time. These are absolutely basic things. So that's, and also when you look at both the Munsell scale and the lab space, to the extent that it's designed for use by traditional painters, the value or lightness dimension is the first and the most important one before you start thinking about the aspects of hue and chroma. So let's start at the beginning. If you want to make a value scale, one of the first things you do is reach for, or the beginner painter might do, is reach for white and black and just mix them and see what happens. And of course, what happens, as more or less everyone else finds out, is that it goes quite bluish. And to explore this, I'll use this paint mixer software that you can find on the Golden Artist website. So they've got all their paints there, and you can mix them in various ways. And it has some numeric results as well, so you can get the RGB values out of there. And that's essentially what I'm displaying in the software that I'm going to be showing you. So let's have a look at what happens when you mix titanium white with bone black. I should just mention here that bone black in this particular acrylic range is what the oil painters would usually know as ivory black. And to get used to how the space works, there's the lightness axis. We've got the bone black hiding there slightly behind the lightness axis. Titanium white is not a precise white. There's a slight hint of yellowishness to it. So let's get the down view, and you can see that there's a slight bias to the yellow side with the titanium white. And then when you mix them, you can see the mixing string, as we already saw, was quite well behaved, and it's got a very specific blue bias. And this is not something that happens just with bone black. It's not as though it's something particular to bone black. So let's try another black here. Say carbon black. And you get essentially the same kind of interaction. In the case of the carbon black, it probably goes a bit bluer, but the pattern is the same. And so the question the obvious question is why is that happening? And part of the explanation was in that graph that I showed displayed much earlier on. If we go, there's this rush back here. Looking at all the blacks are pretty similar. Even though the gap between their scattering and absorption is very constant, which gives us this nice flat, low reflection, the actual levels of scattering and absorption are different depending on whether you're on the blue side or on the red side of the spectrum. And when you start mixing it with the titanium white, and indeed with other paints, the fact that the absolute level is different between blue and red suddenly starts playing a role. So I can demonstrate that in numbers, or you can maybe just take me at my word that that's what happens. And it's the reason that in something like the Zorn palette, people quite often simply uses the black as a kind of a very weak blue. Let me just find my point in my mouse here.
Excuse me, Sean. Is it
Sorry.
possible for your screen to be enlarged a little bit more? I know you need to access your desktop. It's just that it shrunk a little bit from the previous presentation.
You mean the actual PowerPoint part of it?
Yeah.
Yeah. Okay. I'll try and enlarge that a little bit.
There was just a commentary. Yeah.
Yep.
That it's
Yeah, for sure. Yeah, we'll do. I'll try and drag this a bit further out of the way. So in fact, this raises one of the first questions, which is if you wanted to have a proper neutral value scale, what exactly can you do? And for these purposes, what people quite often do is try and find a paint that goes on the opposite side. And a number of them do this, but Umber certainly does that, but I'm just going straight to the most efficient one, which is raw umber. So in this case, we've got a mixing series between raw umber and titanium white. And if I show you the view from the top, looking down, you can see that at least in perceptual color space, you've got this almost perfect opposition between the raw umber and the bone black. So you would suspect from this that if you mix them in the correct ratio, you can get something that simply travels straight down the middle. And that is in fact the case. If you look in this particular series, I mean, I can't show you the composition here, but so for example, we just plot the neutral gray. You know, that paint, if you look on the label, you will see it's actually been mixed. It's a mixture of titanium white, but it actually might be carbon black, I'm not sure, and raw umber. So that helps us establish a value scale. That's fundamentally, we're going to be using some mixture of bone black and raw umber to move up and down this value scale. And for the rest of this presentation, I'll just, for convenience, use these grays just because, you know, in this particular case, they're pre-mixed and it's too complicated to talk about mixing the black and the raw umber every single time. Right, so moving back. So the first, having established a value scale, we now get to tinting, which is mixing with a white paint. And most of the way through, I'm going to be showing this both for inorganics and organics. They actually act reasonably similarly, but it's partly to give you an ongoing commentary that you've got a feeling for the difference between those kind of families of paints. So let's open up the inorganic one. Here's one I prepared before. I think. Yep. So there's quite a lot happening here. So in this case, I've used, actually, I was discussing this with Veronica before the presentation. Not many people are necessarily familiar with this bismuth vanadate yellow. It's very similar to cadmium red, cadmium yellow light. Absolutely beautiful inorganic pigment, very, very permanent, and a good cadmium replacement. So I like referencing that. And it acts in a fairly similar way. Yellow ochre, everyone is pretty familiar with. Cadmium red mid is something many people would use. Various oxides, ultramarine blue, cobalt turquoise. I actually forget what I put down there. Oh, that's a cobalt green and a chromium oxide. So this is the view from the top. So let's see what's happening here. Quite typical for the yellows. You get a slightly curved path. Now, what a curved path means is that there's a slight hue shift on the way in. So there's a slight move to something that is a bit greener, but not terribly. Ones like this yellow ochre, almost straight, but again, there's a slight move to something slightly cooler. The ones that are most spectacular are, as I referenced previously, the reds, cadmium red medium in this case, which is just an absolutely astonishing kind of twist towards the magenta side. So let's just turn this upwards so you get more of the maypole effect happening. So you can see in terms of value, it's sort of nice, fairly straight steps up, slightly bulging in the case of cobalt turquoise. But really, the story here is the one about the hue shifts. In the case of ultramarine blue, it goes over very slightly to the greener side compared to its slightly reddish start. And then in the case of the cobalt turquoise, you've got the opposite direction. So this is one of the first things that you need to understand, that people quite often want to raise the values of whatever paint they've got, local color they've got. And they simply add white. That's not a crazy thing to do, but you need to be aware that there are going to be hue shifts, and in some cases like the red and the ultramarine blue, quite strong hue shifts. Let's have a look at how this works in the organic case. So for the organics, I have selected this benzimidazolone, I think is the full name for it. This is a relatively modern organic pigment and a really fantastic yellow. I certainly prefer them to the Hansa yellows that, as you saw earlier from the Sarah Sands graphs. I'm sure they're very good modern ones, but I just steer clear of them, and so I prefer the benzes. Pyro orange and red, these are organic pigments that definitely come out of the auto industry, and really beautiful chroma, beautiful pigments to use, developed partly as a replacement for the cadmiums. And again, they do exactly the same thing as the cadmium. So if anything, a bit more, just a spectacular move to the magenta, slightly more purplish side as they mix with the white. Medium magenta in this case, this is a bit of a convenience pigment, or convenience paint. So when I started off and sort of putting together my own palettes, I think I felt very strongly at some point to just have paints with a single pigment in, on the basis that surely I can, the whole point is that I can mix everything that I want myself, and I need to learn to do that, and that's fine. The convenience mixes are, it's pretty much what it says on the tin. It is really convenient sometimes to have one like this, where it's clearly been a combination of an organic pigment that's much darker, and it's sort of been caught at its highest chroma mixing point with titanium white and sold as that. So absolutely, you don't need to do that. You can buy Quinn magenta and mix it in, or you can just have that one. And already have it at its maximum chroma point. Now, we've previously seen the extreme moves that you get with ultramarine, and if anything, this phthalo blue-green shade has an even stronger move in hue. So that's an absolutely enormous move. So if all you wanted to do was to raise value and not change hue, you've actually got quite a lot of work to do. You might have to have actual strings of these paints next to each other and create a joint string to keep your hue constant. So this is already one of the basic things we need to think about when we're doing tinting. Moving on to toning, onto shading. Let's get back to. So the natural thing again for the painter in the beginning is that you want to do your shading with black. But as we pointed out right at the beginning, black has this bluish bias, which changes everything when it comes to shading. So let's try this one. Try to keep this relatively simple. So you've got a bone black as your shading pigment. And when you mix it with the cad yellow, you get green. That's the biggest worst shock for the beginner painter. They wanted to shade the yellow, and they wanted to maybe get a dark a greenish brown or a reddish brown if they're mixing something more on the red side, and instead they get this green. And we've seen the bluish character of the bone black now, and it's most clearly demonstrated in this mix with the cad yellow. If I turn this on its side and look what's happening on the dark side, you can see these, generally speaking, straight paths. But the cobalt teal here, cobalt teal, by the way, is I mean, it's a very expensive paint, but it's an absolutely lovely paint. But look what happens to it when it gets mixed with the bone black. You can see how instead of going down in a straight line, it goes closer. It's got this kind of fluted effect going straight to the center, which means essentially that it loses chroma pretty quickly. And that's a fairly characteristic thing that happens with quite a lot of pigments. And that's a difficulty with shading series, because normally if you're a representational painter, you're using shading series to represent the turning of a form. So this might be your local color. This is what we think of as the real color of the object. And then as light decreases and you start shading it, you might have just wanted to mix it with black, but you find that you're actually losing chroma too quickly. So sort of a technical aside here, one color term that David really emphasizes and that really everybody should know if they're doing this realist painting is saturation. And saturation refers to the straight lines that run down, and in fact they point somewhere a little bit below the absolute black, and that would be the actual path in color space that a theoretical shading of a cobalt teal local color would take. So relative to that, you're losing a lot of chroma, and to the extent that you're losing chroma, you would lose the realism of your representation. And that is one of the reasons why the very dark but highly chromatic organics are very useful. So if you find something that is, you know, sitting down here in color space, but is chromatic enough, and you can mix it in to pull this path closer to the actual constant saturation path, you'll improve your representation. Looking at the cad red, it's got a very nice straight path. It doesn't quite have as bad fluting as you have with a cobalt teal. I think this is partly because partly because of its opacity. The opaque pigments tend to act a little bit better in this respect than the more transparent ones. So having said that, let's have a look at the shading the organics. And here we go. So again, we've got the benzy yellow. Let's go straight around to looking at what happens with the yellow, and you see, well, it depends a bit. It's actually got quite a nice straight line as well. And the Pyro orange acts fairly nicely as well. I think the medium magenta is definitely showing the fluting I was talking about. And then here's a phthalo blue green shade. You can see this is one of the chromatic ones. It's almost as dark as the bone black itself. This is a very helpful one to have down here and to improve your saturation when you're doing various mixes. Interestingly enough, this is just teal. I think in this range, what they're trying to do is to create something that's much cheaper than the cobalt teal, but acts like it. And you can see it actually does that. It is similar kind of chroma, and it acts similarly badly with respect to the bone black. You've got this incredibly fluted kind of effect. So you definitely will need, if you wanted to do a proper shading series here, you'd probably need some dark organics as well. Now, I should go back at this point. We've now seen that shading with bone black gives you these massive hue shifts, especially with the yellows. It's clearest with the yellows and to an extent with the reds. So that should tell you that we need to investigate other colors for shading, and so, or other paints for shading. So I'll just show you the shading series with umber. So in this case, I'm using raw umber as a shading. Now, of course, in some sense, it's obviously wrong, because ultimately you want to reduce the chroma to 0, and raw umber has a great deal of chroma in it for its lightness. But it improves the hue shifts that you get from mixing with yellow and looking at the cadmium red dark as well. So it's not nearly as pronounced. It's still not perfect, but it's much better. So that tells you that when you are working on shading, whatever your palette is, whatever lighter paints you pick to kind of populate your palette around the hue circle, you will want to shade at some point, and you will want to think about that process of shading and not just confine yourself to bone black or raw umber for that matter. It's probably a combination of the two, and possibly some other high chroma, very dark colors to get your saturations right. So those are the two paint combinations that gives us shading and tinting. The last step is the one where we need to change chroma. So we can go up in color space, we can go down in color space. Now we want to go across in color space. And let's do, we probably have, I'm going to end up having time issues, so I'll just do one representative one here. So what I've done here is, this is obviously a set of organics, and in this case I did include the hand, so they all act fairly similarly as far in this respect. And turning color space here on its edge, I've just roughly matched up a gray with each of these paints. So the teal is roughly value 6 in Munsell scale. This viridian hue is roughly Munsell 3. The Pyro red is roughly a Munsell 4, and so on. And so this is a fundamental way of reducing chroma. You simply pick a gray of at least the same value, and you create your mixing string. And the single point that well, there are two very important points here. One that hasn't come up before is this clothesline effect. So David talks about that a great deal. You see it very clearly here with the Pyro red, which is, it's roughly value 4, but the mixes have a much lower value. So if your interest is in reducing chroma but keeping value constant, you've got a little bit of a battle on your hands. You probably, if you're trying to, your target is somewhere over there, you might want to start with a lighter neutral gray and get that sort of mixing curve. But the first thing to be aware of is that there's a drop like this at all, and it's very pronounced in the reds. It also happens in the yellow, but to a lesser extent. So this one is a little bit difficult to match the values precisely, but you see there's a little bit of a drop. In this magenta case, which is obviously which is close to the reds, you see the drop very clearly. And this happens whether it's organic or inorganic. So yes, using the neutral grays is a good way to reduce chroma, but you've got to manage your values. And of course, you still have some hue shifts. So it's not quite as dramatic as it is with pure black, but you can definitely see hue shifts come into it as well. Okay, so those are the fundamental tools we have for moving around color space, apart from directly mixing the chromatic colors with each other. Now, something that comes up quite often, people ask, can you do this graying out with complements? And the answer in some sense is, of course, yes. So what I've done here is taken a cadmium red light and mixed it with various other pigments on the other, so with various other paints on the other side. And this is very characteristic for the mid reds. You've got this incredibly strong fluting. I think David's image for this is something like an octopus, a shy octopus in this case. It's not spread out at all, but it's very thin and pointy. So for this very wide range of paints, it's possible to mix. You know, these ones are obviously not neutral, but they're really quite close to neutral. And for a couple of these, you get very good grays. So in some sense, that's a good thing. You know, it's easy to neutralize cadmium red, and you can do it in all sorts of interesting ways. You can produce very interesting grays, which is a whole different topic. But at the same time, it's a little bit alarming as well. It means that the cad red just doesn't make chromatic mixes. If you want to maintain chroma, you sort of want to go at least in a straight line or around the outside, but instead you've got this fluting effect. And that's going to play a little bit into our design of palettes, or our thinking about palettes. In contrast, if you do the same thing with magenta, so here I went a little bit crazy. I'm sorry. This is there are lots of scribbles on this one, but I tried to neutralize the medium magenta. So I thought surely I should try pretty much everything on this side, and I literally threw all the pigments that I could think at the medium magenta, and clearly one or two of them managed to get neutral grays, but by and large it just wouldn't do the same thing as the cad red. It either had a more chromatic mixing path like that one, or a straight path, but there was none of this kind of collapsing in towards the center. Fundamentally, the reason for this is that the magenta, it's like the M in CMY printing. The magenta has blue and red light in it. It has more color, and so it loses color. It's harder to cancel it. You know, you can go over to the bluish side, or you can go over to the yellowish side. All sorts of things can happen, but to precisely cancel it with a very narrow green is very difficult, at least in the pigment world. So keep going around. So we've done cad red, now we've got magenta, now we've got cobalt blue. And there is method to this madness, because this is all really relevant when we're thinking about how we want to put our palette together. And cobalt blue, hue in this case, but cobalt blue itself does the same thing, acts very much like the cad red did. Again, you get this very, very narrow spread and a huge range of paints. Well, maybe the green gold is exaggerating, but a significant range of paints here, which gives us very neutral values. a very neutral chroma, I should say. Keep going around the hue circle, this time the cobalt teal, and what a contrast. So yes, the cobalt versus pyrrole red, definitely, that hits it just about properly, and you can get something that's almost a neutral gray. But for the rest, you can see it really stays away, and it gives us very chromatic mixes with virtually everything else, and absolutely beautiful greens when you mix it with the yellows. In contrast, if you remember with the ultramarine blue, when it mixes with the cad yellow, it just runs along there, much less chromatic. So there's a sort of a pattern emerging here. The mid red doesn't work very well from the point of view of maintaining chroma. The mid blues don't work very well. The magenta works very well. The teal work very well. So we can sort of see where this is going, and I should probably skip straight ahead to that. This would be a very simple palette. So forgetting for a minute about the whites and the shading colors that you have in there, if you're just talking about the chromatic ones, if you have the traditional so-called, I don't know who ever thought this is traditional, but it's apparently traditional. Red, blue, and yellow is a good palette. And yes, it definitely travels around the hue circle. You cover, in theory, you cover all 360 degrees of hue. That is definitely true. But the chroma at which you get it is just wildly different. And in particular, you can see how the cad red and the ultramarine blue just produces absolutely, I don't know if there's any other word than pathetic for these purple magenta type hues. And the greens really are not wonderful either. In contrast, so I can actually get rid of this one because in the next one I've put the two together. So we had the cad red, cad yellow, and ultramarine blue. If conversely we stick with the yellow, because yellow has a lot of reflected light, it reflects all the greens and the reds, just like magenta reflects yellow, reflects blues and reds, and the teal reflects greens and blues. Those three give you a very nice wide range or wide gamut, and they mix in a way that preserves chroma as much as possible. So the good thing about the so-called CMY palette in this case would be obviously in this red area and in this green area where the contrast is enormous. But I do have to point out something else as well, which is we're missing out that little triangle there. If you want a high chroma red, you just can't get it from yellow and magenta in whatever form, or it's pure quinacridone or whether it's this kind of convenience mix. So if you actually want a proper red, you can't get it. And to an extent, it's not entirely clear. Maybe if we mix in, let's see, titanium white with ultramarine blue. So again, you get really fantastic blues with just a little bit of white added into the ultramarine. So I would not necessarily be in the camp that says red, blue, yellow is silly and CMY is the only way to go, because your pure blues and your pure reds are getting lost in the process. So depending on whether you want to work with a very limited number of colors, then it starts depending on your application. If you're happy to live on that side of the color wheel a lot of the time, then RBY would actually work quite well for you. If you really want to cover more of color space, much better gamut, but possibly miss out on some intense reds and blues, then something like this would be better, the CMY. Of course, you can just combine them if you don't mind having more paints in your palette. And I don't know where there's a formal definition for split primary, but this is something like a split primary. So you've got a very warm red, and then very cool one, obviously, slightly reddish blue, greenish blue. You don't need to split the yellows. I mean, these yellows are all fantastic, but I did it just to show with the CAD yellow primrose, you get this truly amazing greens. So this is a really a very wide gamut with 6 paints plus your shading and your tinting. Paints would probably be titanium and at least raw umber and bone black in this case. Having said that, I think very importantly, you can easily get the idea that that the chroma is all that it's about, and it's when you're designing a palette. And that's obviously not true. The application is also really important. So some painters, not all painters, but some painters like the Zorn palette, especially for portrait painting, figurative painting, and with all those amazing gamuts we just saw, this looks almost strange. You literally have yellow ochre, CAD red medium or mid, and carbon black in this case. So that supplies your very weak bluish side. But overall, this entire pyramid of color, tetrahedron of colors, sits almost entirely in just that quadrant of the color circle, of the hue circle. And of course, we know from these paintings and the paintings of other people that use this limited palette at the moment, they can do absolutely beautiful figurative painting, because much of what they do is happening precisely in this quadrant. And furthermore, I've been talking a lot about individual colors, but painting is about color relationships. And even though the blues are relatively weak, once you put them into context of quite chromatic opposing colors, they can pop quite a bit more as well. So you can get the illusion of having stronger blues than you actually do if you're painting well. So this is why I said in the blurb to this, I'm fairly agnostic when it comes to palettes. I just want to show to people what the different paints do, what these mixing paths look like, alert them to issues like the fluting when you go down to carbon black, and that you need to think a lot about your shading colors and so on. So I see where I've got 3 minutes to explain all of color mixing to you, or color matching. So that might be an interesting challenge. So trying to put together the tools we've developed here to match a single spot color. And so what I've set up here, this is one I prepared before, and I obviously, this is one that works easily and well because I'm trying to explain the principle. I've set it up so there's a particular target color, which is a yellowish green, or a greenish yellow, if you will, fairly high chroma. And I want to match that. And I'm assuming that in my palette, I have a cadmium yellow light and a permanent green light. So the first step in the matching process is to look at the hue that I'm trying to match, and to, in my palette, find paints that bracket that hue. So one's slightly more greenish and one that's slightly more yellowish. And these are going to be my colorants, or my chromatic paints that are going to be the backbone of trying to do this matching. So that's step one. And I have the full 3D version of this here. So I'm going to go through this in 2 different ways. I'll show it to you on these flat snapshots first, and then we can look at the full 3D representation. So the first step is bracketing the value, bracketing the hue, sorry. The next step is to match value. So what I want to do is each of these paints that I'm going to use to get to my target color, I first want to bring them to the same value as my target color. You can probably see it most clearly here. The target color is roughly at a 6 or a 7 in Munsell scale. So I need to bring my CAD yellow down in value, which I do by mixing with my shading color till I get to the same level. And I need to bring my permanent green light up in value. So I'm tinting it. And because this is one I engineered, I happen to have two of my larger beads that are exactly lined up properly. And here's just another 3D view of it. There's my target color. And I've shaded my CAD yellow, and I've tinted my permanent green light. And now I don't care about these ones anymore. The original ones, these are now the colors that I'm going to use to try and get to my target. So I've matched the value. And if you think about all the scenes I've flashed in front of you, you know that hue and chroma is all over the place when you do mixes between two colors. And as painters in your training, you spend a lot of time learning to match values. And the way in which values change are fairly predictable once you've done these tinting and shading series. So this is this is a very natural first step, is to first match the value, not hue or chroma. You can do that next. So we've got our two mixes there, which is the shaded CAD yellow and the tinted green. And now we want to match the hue. So we want to mix this one with that one and get something that matches our target color in hue. So matching in hue means that basically it lies on this radial line going through there. So, and this step, matching hue by eye, especially when the hues are far apart, is actually much harder than judging value, or at least it is for me, and I think on average for most painters. So this is one of the reasons why get the value out of the way. And now in this case, because I engineered the example, it should be relatively straightforward to mix this very slightly greenish yellow with this very bluish, well, bluish green almost, and get something which matches up in hue. And now the last step in theory is very simple. We're very close to where we want to be, but we're slightly too chromatic. And we know how to solve that problem. We just add a little bit of neutral gray of the same value. So here we go, that neutral gray mixed in with our correctly hued mix would give us one that now matches in hue, value, and chroma. Of course, we know in the real world, sometimes that distance is not going to be so short. We know about the clothesline effect with when we're reducing the chroma. So in fact, in practice, we might often have a slightly lighter gray that we use to do this final chromatic matching. I'll just do this in 3D. How did that happen? There we go. There we go. So that was our original target color. We chose the bracketing paints. We shaded one to get down to the same value, and we tinted this one to get up to the same value. So we had these two mixes. Then we mix them together, matching hue. And then finally, we use a little bit of gray to get us to our target. And so that's all fairly intense. So I guess I can finish off with something a bit lighter. This is the rhyme, really. You bracket the hue, match the value, match hue, match chroma. Be very happy creators, and thank you very much for listening.
Thank you so much for that. That was great. We do have a few questions.
Sure.
This is Renee Bayer. Are the tints in lab space published somewhere for the artist reference so that they can correct for hue shifts?
I believe so. So on the actual the mixer on the Golden website, whenever there's a mix, a sort of a current mix on your palette, it automatically displays the tints. I think that I forget what the ratios were that Golden used for that. So it shows the tints on screen, but it doesn't actually give lab values for each of them. So you'd have to do those one by one and read off the RGBs and so on. It's probably easier to just judge it by eye, because they are nicely lined up. They do touch each other, so the color comparison is fairly easy. But yeah, to do it numerically takes more time.
Okay, thank you. Suzanne Batchelor, are most commercial neutrals by Williamsburg and others using ivory, black, raw umber, and white?
I don't know, to be honest. It depends a little bit on the precise pigments that they've got available. I think one of the things I didn't touch on is the fact that just the chemical designation of the pigment doesn't always tell you how it behaves. Everyone knows that they've seen pigment numbers that are the same, and yet the paints have quite different hues. Yeah. And that quite often means just that. So a simple example might be red oxide. It used to not be possible to produce nanoparticle red oxides, but it is now. And so you get these amazing transparent oxides, which are much more modern and in fact act a lot more like organic pigments. And all that's changed is the pigment size. So the short answer is it depends a little bit on which pigments are available to each manufacturer. But they do disclose what the pigment numbers are that go into the neutrals, and you just have to follow that manufacturer by manufacturer.
Peter Donahue, if after we match the hue in step 3, we have less chroma than the target, are we out of luck?
Yes, in short.
Yeah.
Pretty much. I mean, it depends, because you saw, for example, that the organics, when they go into tints, they can have these massive explosion in chroma. So it's possible that you picked the incorrect bracketing pigments or bracketing paints at step 1, and that somewhere in your palette there's organic hiding, that when you add a bit of white to it, it suddenly gives you the chroma that you need to. So you know, that is where a degree of judgment comes into picking your bracketing paints. But yes, if you've got a certain limited palette and you're trying to match a high chroma color, sometimes you just can't. And then you can say the best you've done is you've matched the hue and you've matched the value, which is most important. You've matched the hue and the chroma. Well, you're going to have to make it pop somewhere else by putting it next to an opposite color or something.
Yeah. Renee Bayer again. How is it best to correct for shift when mixing cad red with white? Which color would you use?
Well, I think pretty much anything that is more on the orangey side, and you know, at worst case scenario, yellow, but certainly something on the more orangey side, like a burnt sienna or something, might help. Depends on the chroma you're looking at. If you're looking at very high chromas, then yeah, it might even be a mix between like a cad orange and a yellow, depending on how far out you are in your chroma. And again, I should emphasize, it depends on the particular manufacturer. So for each of them, that particular curve, it's going to be qualitatively the same, but not quantitatively. So, you know, you'll need to do slightly different adjustments depending on that.
Lots of wonderful thank yous have been posted, but
you.
that's, yeah, you've done a brilliant presentation. That's it for the questions at the moment. Does anybody else have a question before we wrap it up? I think we're good.
We're good. Thank you very much, Veronica. I'll just share my screen one last time. I think we'll be talking about what comes next in a couple of different senses. But certainly in the series that we're presenting, the next educational talk will be by Dr. Mark Liu. And the general topic area would be modern and ancient dyes and how to use them sustainably. So obviously dyes and, thinking about clothes stuff and so on, and the clothing industry, generally speaking, is massively important and very interesting, especially when he talks about it. So we haven't fixed the date for that yet, but just generally keep an eye out for that upcoming talk in another couple of months. So I think that's is that back to David now?
Okay, thanks, John, and thanks Veronica for that presentation, which is really beautifully illustrated. Fantastic to see those principles illustrated in with your wonderful new software. I saw someone asked, is it available just then? Just then, are you any plans to make that available? Or
well, I actually would love to. I must admit that when I started preparing the talk, there were a couple of other software packages that I'd seen used before, but they're sort of aging now and don't necessarily work with modern operating systems and so on. So really, I created this from scratch just for the presentation. So I'm hoping to develop that a bit, and yeah, possibly somebody's interested to put it out there. So I'm glad at least that there might be a demand.
because you're working on a Mac, aren't you? And I don't think there's been similar thing for a Mac before.
Not really. I mean, you can use a color inspector, for example, and like that software that Philippe Calantoni wrote in France. That's really fantastic. But then again, sometimes the pure color theory perspective is a bit different than the painting perspective, and so it's useful to have something that's custom written for that.
Good, great. All right. Well, I've just got three quick announcements or comments just to finish. Jean mentioned that this color matching process is ultimately based on Frank Riley, an American illustrator and influential art teacher from the mid-20th century, and we've actually had a wonderful presentation on Riley's whole approach given by Tristan Elwell earlier this year, and that recording is available on the Colour Society of Australia YouTube channel. It's really quite fantastic. It goes into a lot of information about that approach that is you just won't find anywhere else. So have a look at that if you're interested in the background of this method of matching color by thinking in terms of the Munsell framework. Secondly, we must mention our Colour Society of Australia conference coming up in October, 12th to the 15th, which will be run by the Western Australian division and a hybrid online and in person. So, I think there'll be information about that and registration opening this month sometime. And finally, our next presentation of the New South Wales division will be in about a month from now on August 27th, and we'll be hearing from Michael Mentler. And Michael Mentler is a fascinating character. He's trained as a sculptor, but also well known as a master figure draftsman and teacher of life drawing and anatomy. And but he's talking for us because he trained under a sculptor called Werner Drews, who in turn trained at the Bauhaus in the first years of it under Itten and Kandinsky and Klee, and he kept up a correspondence with Kandinsky for several decades after that time. And so Michael will be talking about, he's titled his talk, the Colour Circle at the Bauhaus and Beyond. And I think he'll have a lot of wonderful insights into those very important teachers of colour. So I'm really looking forward to that. So that's all from me. So thanks once again, John and Veronica, and hopefully we'll see you again in a month. Okay.
Thank you. Bye-bye.
Thanks, everyone. Thanks very much for coming.